Day 753 off the grid, and we're in the laundry and I'm looking at the control panel to the left there, and just to the right the little DC distro there, 12 volts. But what we're really here for today is to look at this. It's the new WeHouse charge controller. Now, the title of this post may have been somewhat clickbaity. How can I call this a model DC grid tie? Well, it's quite simple. It's connected up like a grid tie and it operates in much the same way. I'll explain. 12 volts comes from the main power room, of course. There's a line that comes from the main power room over to here. If we consider that 12 volts the grid, the way this is connected in the house is much like a grid tie inverter would be. So what we have is we have 12 volts coming over from the shed. Yes, there are batteries over there, but that's irrelevant for this discussion. There's just a wire which comes into the house here. This little charge controller here is connected to a solar panel up on the roof. In fact, right pretty much on the roof above me here in the laundry. And the battery connections there, of course, are connected to that fuse there, which is connected to this battery bank through that big wire I've just been talking about. So yeah, it works like a grid tie. When the panel, which is a 10 watt panel, is connected here and there's power going through it, power will come down from the roof, go into this charge controller, and then flow out, of course, and unite here in this distro board. If there's any loads in the house that want that power, power will flow into the house and power the loads, the 12 volt DC loads I'm talking about. But if there's any excess current, it'll instead flow back down the wire to the shed. And of course, at night, when the sun goes away and the panel is disconnected, all the power will come from the wire from the shed. So yeah, it works just like a grid tie, except in miniature. And admittedly, of course, it's all DC. There's no inverter involved, but the principle is the same. When the voltage here is higher, this will supply the power first to the loads inside the house. And when the voltage here is lower, it will pull power from the cable. So it's kind of interesting, eh? It's kind of a good thing for the kids to see in operation, because with all my stuff out in the shed, there hasn't really been an opportunity for them to fully observe it. But we've got that out of the way now, the whole sort of miniature model grid tie thing. But why have we got this? Well, notice this cute wee charge controller. It's in the shape of a little house. It's even got a chimney, which I believe may be the temperature sensor. And it's got this Volks solar panel here on the roof. So it's kind of like, you know, it's cute basically. What happened was I was looking through eBay because I was after a sort of a low profile, well, small charge controller for my main board out in the shed that showed all these metrics, you know, volts and hopefully amps and stuff like that, you know, for the extra solar panel that's on the A bank. But I ran across these and Bethy thought they looked really cute, and she likes things that look cute. So look, it's got a little sun on it and stuff like that. So I had to buy it just for that. And then it was like, well, oh, so you're just going to go and put that in the shed and we'll never see it? I said, oh, no, I'll put it in the laundry. And so basically I got this, decided to put it in here, and then I had to find a use for it. Basically, I had to find a use for it, you know. I thought, well, it's got quite a sophisticated load controller here. It might be about time we make the lights automatic. And as you'll see, the switch is now set to auto for the ceiling lights. Up until now, every night we'd come here and flick that to manual, which is basically on, which fires up the lighting inverter. And every morning I'd come out here and turn it off. And I'd always be meaning to automate it with some kind of dusk sensor. So this gave me the opportunity to do it. It's kind of done in style, done in overkill. in a way. So instead of having a little LDR and a little dusk sensor circuit, we've got a whole 10-watt solar panel and a charge controller going on to do the same job. But it does it really well because the way the switches, it switches in 3 stages. So you would never end up in that situation that you can do with simple dust sensor circuits where it can oscillate between on and off. And I mean, that's bad enough if you've got it fed to a filament light bulb, but you don't want to have your lighting inverter being rapidly switched on and off, fluttering, you know. It would probably wreck it. So with this, that can never happen. So that's one good reason to use it. Now, of course, the 10-watt panel is really up there as a pilot panel. It's just really an oversized dusk sensor cell. But, of course, I'm not going to waste the power that it's making, so it still is connected to the system, as I've outlined at the start of this video. Now, there's a big problem in using solar panels and charge controllers as dusk sensors. Although a lot of these small 10 amp ones offer that facility, the problem is that they don't switch until nigh on full darkness. I mean, that's how long a solar panel can keep pumping out voltage. Not any useful current, but once the solar panel's disconnected from the battery, then its voltage can actually stay quite high until it's rather dark. And so these things will usually consider it daylight until it's almost pitch black. It's ridiculous. It might be alright if you're just using it to switch an outside light on or a garden feature or something like that, but this of course turns on the lights essentially in our house. Well, through the inverter of course. So it's got to switch on a lot earlier. How do you make it do that? Well, one thing you could do, of course, quite simple, is that you could load down the solar panel with some kind of ballast load. You could put a resistor across the solar panel inputs here. Well, not literally here, but you know what I mean. Across these solar panel inputs, you put a tail light bulb or a torch bulb or just a resistor. You know, anything that's going to make the solar panel work hard. So then, at the end of the day, as the current falls off, the resistor will cause the voltage to fall off, and that will work. But the problem with that is that all throughout the day, when the sun's shining, you're burning off all that potential power that you could store or use in this dump load, basically, which would be kind of wasteful. I came up with this little circuit here. You've probably been looking at this throughout this video with me prattling on and wondering, well, when's he going to get to this? What's all this about? Well, this box here, of course, is a miniature version of what you would most certainly have with a grid-tie system, or just about any solar system, really. This has got your solar disconnect, which is here, and a fuse, which is a blade fuse up in there, 7.5 amps, in fact, which is underneath the rating of the cable. But, of course, the solar panel could never cause that to blow, because at best it's a 10-watt panel is only going to put out about an amp, but it's there to protect the cable, of course, as we know fuses are for, so it's good for that. But anyway, so yeah, so this box has got, it's got your usual solar disconnect and fusing and stuff, but it's also got this circuit here. And this circuit here is, would you believe, specifically designed to degrade the performance of the solar panel. You're going, what the fuck? Why would you want to degrade the performance of the solar panel? Well, so the charge controller will switch to night mode and turn on the lights earlier. That's why. So basically, of course, if you put the dump load across here, you would be degrading the performance of the solar panel too. Well, this does a similar thing, but in a much cleverer way. If you look in there, there's a MOSFET transistor. That MOSFET transistor is actually run in a linear mode, and it's fed through these Zener components, which this LED and this actual Zener diode, through a voltage divider. So what happens is, near the end of the day, when the voltage starts falling from the solar panel, this transistor starts to turn off. So it basically makes the process of the voltage diminishing at the end of the day very rapid, much faster than it would normally be. And with this trim pot here, of course, I can control that process so I can adjust the point that happens. So it basically gives me an earlier turn on, a turn on at a time when we would want it for the lights in the house. So that's essentially what that circuit is all about. It's quite a simple circuit. Oh, and in case you're wondering, the energy harvest is probably not diminished much, because this only really kicks in at the end of the day when you've got the situation where the solar panel's not delivering much useful current anyway. So if you looked at a graph of the energy harvest, you'd see that this would only eliminate a little bit at each end, so it doesn't really impact that much. But anyway, it's only on a pilot panel anyway. It's not like it's on my whole solar array, so that doesn't really matter. That's what I've done on day 753. In order for it to switch this, I had to make up a relay unit that's inside this box, which I'll throw a video of that on at the end of this. And also I'll throw some video on of the actual solar panel mounting that I did. Yeah, because the thing is, these charge controllers of course switch all the negatives because they use N-channel MOSFETs, so the positives are all common and the negative is actually the switching pole. In my control unit, of course, I switch in the positive, so I basically needed a relay unit to sort of invert that. I could have done it solid state, but I decided to go for the relay, which you'll hear about when I talk about it in the supplementary videos. Oh, and I'll also throw in the schematic of this too. But bear in mind there is an extra 10k resistor wired directly across the solar panel input that you won't see in the schematic because I added that later. That's just to make sure the voltage sucks down at the very end. So that's bye from me for now from day 753, and here's the supplementary videos. I really wanted to do a shot of the little relay box before I case it up. This is going to be connected to the load output of the WeHouse charge controller, and it's what does the business of automatically turning on and off the lighting inverter. Originally I was going to do a solid state thing here with a transistor and a couple of resistors, and I could have, but the problem was the load output of the WeHouse controller always has some residual voltage, and for most loads that wouldn't matter, but it was just enough available sinking ability there to keep a PNP transistor turned on, unless you took measures to deal with it. And that could have meant a few trials and stuff. So I found that I had to sink that current through a 560 ohm resistor, and by the time you start putting current through a resistor like this just to burn it off, you might as well put current through a relay coil, which is going to work first time. And furthermore, it has another advantage, that it's also got the normally closed contacts. So I wired up this handy little relay unit. This is a DIN rail mounting box. Here's the cover. And I was very pleased with this because I didn't need to use any hot melt glue or any other methods for mounting the relay in. The electrical connections are also the physical mounting, as you can see. So what we've got is we've got 4 sets of terminals here. The upper and lower ones are just a pass through here. So this is going to be the power which actually runs the control box in the laundry. And of course power is taken from it into the common switch contact of the relay switch. And there it goes from the normally open and the normally closed to the set of terminals here, which I've marked with a little moon and a little sun and a little positive sign, because that's positive voltage. It's connected directly to the plus supply. And then we've got, of course, the coil voltage, which is also marked with polarity because I've incorporated a diode in across here. And I always do that because you just never know when you're going to connect a relay to something and the reverse impulse spike is going to upset whatever you connect it to. I don't know what protection the WeHouse controller's got in it, so it's not a big deal to wire a diode in. But it does mean, of course, you have to be conscious of polarity when you connect up the relay, when you otherwise wouldn't have to. But, you know, that's good practice anyway. So, yeah, pretty pleased with that little unit. Choosing the relay, like I said, makes it a bit more versatile. And it can probably handle a bit more current because I don't have to worry about heat sinking or anything like that. I think these relays are good for up to about 5 amps, which is way more than I need for this. I mean, at the moment, it's only control currents. I don't have any
immediate use for the normally closed contact, the daylight position, but you know, it could be handy if I do in the future want to switch something on during the day as opposed to off, you know, like a fan or something like that, who knows. But anyway, I'm going to carry on and get this installed. And here's the solar panel that I'm using. Obviously I filmed this earlier, but I just wanted to show you the panel before I put it up on the roof. It's a 10 watt panel, as you can see, and this is the mounting that I've made up. Just some scrap wood that was already cut to these angles, which was quite handy, and a piece of 4x2 down here which straps them together. It's pretty robust, using of course the old bottle caps again as grab washers in a slightly different way, but they work really well to hold a solar panel on. Of course, this needs to be anchored because we do get some high winds, like right now, and this is how I've done it. Again, I've used an old battery as a ballast because I don't want to penetrate the roof up there for this. I just want to weight it down and keep it up there like that. And I'm pretty happy with the scheme that I've used to tie it all together this time. I've actually made use of the battery terminals, which is something I kind of started with those ground mount solar panels where I used the old starter batteries, but in this case I've actually used these screw terminals to attach to this angled stuff, sort of strapping stuff, and screwed in, as you can see. This battery today I just retired from powering the little yellow multimeter on the 24 volt circuit in the solar shed. Its voltage will still hold at about 7 volts, but it's declining rapidly. But if you load it up with a 2.2k resistor, it drops to about 2, so it's not even capable of running a little J-car multimeter that was intended to be run by a 12 volt car remote battery. So it's pretty much past it. And besides, I've got plenty of other near-fucked batteries that can run the multimeter just fine, but this is the only battery I've got available that works so nicely with this mounting scheme, so put it to use here. I think it's more useful. I bought 8 of these in April 2012. They were the first sort of purchase of non-car battery, decent-sized batteries, or reasonably decent size. They turned out to be all pretty much shit. There's only 2 left that are kind of not being used for non-electric purposes. There's one that's running the real-time diversion controller on the 24 volt circuit, and there's one sitting in the workshop ready for some other super low current use, but that's the only 2 left. But I learnt a lot from these batteries. I learnt what you can do to recover batteries and what you can't. So all in all, it was a good learning experience. I might have touched on this before in previous videos, but, you know, I thought I'd talk about it a little. But, yeah, that's the batteries. That's the solar panel mount. I'm going to turn this off now and go and stick it up on the roof.